Good morning, class, and welcome to our grade 11 mathematics class, bright and early at 8 o'clock in the morning.
Mboli, sound.
Good morning, class. I am Miss Shabalala, and welcome to our grade 11 maths class, bright and early at 8 o'clock. Remember, we are continuing with trigonometry, and you guys can get a hold of me on Twitter at _Mbaliti.
Teacher, sound.
Every time we have new people, we have to keep up with the rules, right? The rules remain unchanged, guys. Respect everyone because we're all here to learn. There's no such thing as a dumb question, and so please ask away. Please type your questions into the Q&A section. Things have changed. We no longer have real interaction, and so please leave your questions in the Q&A section. All questions in the Q&A section will be answered in the last 10 minutes of the class. We will not tolerate any vulgarity. This speaks to point number 1, in respecting each other. Please do not take the opportunity to learn away from someone else. Also, the link to this class will be posted in the Q&A section. So, what are we getting up to today? Remember, we started on trigonometric equations and we worked on grade 10 revision yesterday. We are continuing today on our trigonometric equations and we are looking at more advanced equations. More specifically, what we are looking today is we're looking to determine general solutions for trigonometric equations, and we are also looking to find solutions within a specified or specific interval. That is our menu for today. Right. First and foremost, I'd like to go through the homework questions that I gave you yesterday, our warm-up questions, just to remind you guys about trigonometric equations. I'll go through them step by step. If you have any questions on these particular questions, your point of reference in our Q&A will be question 1 of the homework questions, question 2 of the homework questions, or question 3 of the homework questions. Right. This was question 1 of the homework questions. Sine of 2b plus 45 degrees is equal to 0.123. As I said, I asked yesterday that you guys please bring your calculators because we'll be big on calculator today. And so, first, that from this step, what we look for is we look to solve for our function. We look to solve for sine. In this case, it's sine to the power of -1 times 0.123 on the calculator. That gives us that 2b plus 45 degrees sine is equal to 7.065 degrees. Guys, something to mention. In every exam paper, you get told how many numbers to round off to, how many decimals to round off to. It may be 1, it may be 2, it may be 3. Most of the time, it is 2. And if we had to round off to 2 decimal places in these cases, our number would be 7.07 degrees. From here, as you can see, this is our standard equation and we are going to be solving for b. So 2b is equal to 7.065 minus 45. Remember, guys, what we do on the left, we do on the right. We subtracted 45 from here, and so we remove 45 from here as well. This means 2b is a negative angle of minus 37.93 degrees, and b is equal to minus 18.97 degrees. As you know, our minus angles to this degree, where they're acute, sit in quadrant 4. Right. Question 2 from the homework question. 2 sine 3 alpha plus 1 is equal to 2.61. You guys remember that, oh, here we go. You remember what you do on the left, you do on the right. So we're looking to subtract our minus 1 over there, and we are going to subtract 1 this side as well, our side as well. And that's how we get to 2 sine 3 alpha being equal to 1.63. Again, then we need to remove the 2, so we're going to divide both sides by 2, just like that. And that will leave us with sine 3 alpha is equal to 1.6 over 2. Simplify that if you will. Eraser. Right. Simplify that if you will, guys. That becomes sine of 3 alpha is equal to 0.8. Our calculators work either way. You could either key into your calculator sine to the power of -1 times 1.6 divided by 2, or you can put it in as 0.8. Our calculators work either way and give the same answer. So then we find that 3 alpha is equal to 53.13 degrees. And then again, this is a 3 alpha. We need to divide by 3 to find a pure alpha. What you do on the left, you do on the right, and we find that alpha is equal to 17.71 degrees. This, guys, is question 2 on your homework questions as a point of reference. The last question, question 3, tan 2c is equal to 3.123. Very straightforward. We're going to put in our 10 to the power of -1 times 3.123 in the calculator, and we get a value of 72.24 degrees for 2c. This, guys, is the angle. We divide both sides by 2 to solve for c, and we find that c is equal to 36.12. That is literally straightforward. That is it. That is how you solve a basic trigonometric equation. You look to simplify your beta, your angle C, your angle A to the simplest level. Today, though, you do learn that you may want to put in restrictions and conditions. And so today we start with today's lesson. So we use trigonometric equations to find values for the angles, values for your beta, your alphas, that make the equation complete and true. So this means if you can imagine that there can be many angles which make one equation true. Do you guys remember this from functions? Where, our graph could go on forever. We could go back up, down. This could go on forever. Numbers are infinite. And so in our case for now, we've created our graph, our sine graph, where we're saying y is equal to sine of theta. So let's hypothetically say we are looking for sine theta is equal to 1, and we're calling that our econometric equation, and we are looking to solve for theta. From the graph alone, you can already see there is more than one point where sine theta is equal to 1. Right? We have at this point where theta is minus 270 degrees, and another point where theta is equal to 90 degrees. So as you can tell from here, there are many numbers. Numbers go up to infinity. So there are a lot more angles that as you extend your sine graph, you get more peaks, and at those peaks, sine theta is equal to 1. So please pull out your calculators for me just as an illustration. Pull out your calculators for me, please, and find the sine of 540 degrees. Alright, guys, the sine of 540 degrees is also equal to 1. So as you can see, there can be many possible angles and answers for sine of theta being equal to 1, purely on the basis that numbers are infinite. When it comes to trigonometric equations, we'll be doing one of two things, right? We will either be solving all our angles. You're going to be solving for the angles that prove the equation to be true, number one, within a given interval, right? So this would mean that you have said to me that between 0 degrees and 360 degrees, please find where sine theta is equal to 1. And so that changes our answer on our previous page, because at that point, the minus 270 degrees for theta is no longer valid. The theta of 540 degrees is also not valid. Your valid answer is the 90 degrees, purely because you are working within a given interval. Right. In an instance where you don't have a given interval, where your numbers are allowed to run until infinity, meaning you could solve until you turn blue in the face. And so what we do there is we find a general solution. We don't write out specific degrees, we don't write out specific numbers as answers, we find a general solution. And with this solution, what we are saying is, no matter how many times you go full circle around your sine graph, for example, no matter how many times you do a full revolution, every 360 is a revolution, no matter how many times you come back to the same point on your sine graph, your answer will be correct and true for the formula. Right, let's start with working on angles in a given interval. Do these look familiar? So first, our interval, a definition of an interval is really a set of real numbers that lies between two numbers. So we have a start point and an end point. Those are the two numbers, and everything in between there is included in the interval. Some people also refer to all those numbers as a range, right? For those of you who have been to my class previously, who have gone back to these slides, do these look familiar? These should look familiar. These tags here should look familiar, because these were the tags that we used when we were defining each quadrant on our Cartesian planes. More specifically, we were using this tag over here to define quadrant 3. So guys, this is how you express an interval. In an interval, you are saying that you have numbers, other numbers that sit between two numbers, between 270 and 180 degrees. So your 270 and your 180 degrees are starting and ending points. Right. Something to highlight very strictly here is that one would say that I've written the same expression over and over and over again, right? It's looking a lot like I've written the same expression 3 times. Guys, the expression is different, because if you pay careful attention to your signage right here, oh, let me find a different pen. If you pay special attention to your signage right in there, you're going to find that this here interval excludes the 180 and the 270, because it says that beta is more than 180 but less than 270, and excludes them. And how you'd express that in, let's call it trigonometric interval language for our sake, you would write this as beta is an element of 180 degrees up to 270 degrees, with special attention to the brackets. Change pens again. With special attention to the brackets. Our brackets are round brackets. Round brackets exclude the numbers, your starting point and your end point. So what I'm saying to you here is, if beta comes out as 179.9999999, then that is included in our solution. But if beta comes out exactly at 180 degrees, then you do not write beta as 180 degrees, because we have specifically excluded 180 degrees. Right? Looking at our next one over here, this has a different meaning completely to this, because if you check on this second one, we have included our start point and end point, because we have said that beta is more than and equal to 180 degrees. And we have said that, oh, I used 179 as my example. That's not the right example, guys. I should have used 180.111111 as my example. Apologies for that. Okay, and also in this case, as I was saying, if you have, we are including the 180. So if your answer comes back and it's beta being equal to 180, you write that as your answer. But if your beta comes back as 179.999, that is not part of the interval. If your answer in this case comes back as 270, you include it, whereas previously you would not have included it. Special attention to the brackets. In this instance, our brackets are now square. The square brackets dictate that your start point and your end point are included. So in this case, if you get 180 as an answer, when you plug in your formula, then you will be able to write down 180 as one of the percentage, as one of the degrees that you find, because it is included. Right? Example number 3. Work with me here, guys. Right? In example number 3, we are saying that beta is more than and equal to 120, but it's less than 270. So what we're simply saying here is that you will include 120 in your solution if 120 comes out as an answer, but you will exclude 270 if 270 comes out as an answer. So included will be 269.999, but not 270. Hope we are both on track, guys. Any questions you will leave in the Q&A section, and we will have a look at in the last 10 minutes of the class. We'll do a few practice examples around what we do with intervals and how we work with intervals in trigonometric equations. Right? We have our first example here, guys, which says that I'm going to give you an example now, and what I'm saying is that alpha is an element of 0 degrees up to 360 degrees. Number 1, please include 0 if you get 0 as your answer. Please include 360 degrees if you get 360 degrees as your answer. The answer that we are looking for has to sit in between 0 degrees and 360, not more, not less, right? So here is our question, our practice question. The sine of alpha plus 3.65 is equal to 3. The first purpose, or the first intention, is to eliminate anything that is not part of the function from the left side. So we will, in both sides, minus 3.65. Do the same this side, and guess what we come out with? We come out with sine alpha being a negative 0.65. So ding ding, guys, sine is negative. That's point number 1 that I need you to be aware of, that I need you to remember. Let me switch pens for you guys. Sine is negative, right? So now you pull out your calculator and you solve for sine is equal to 0.65. Guys, please take note of this note. When you pull out your calculator to find alpha, this alpha is what we refer to as a reference angle, or angle, a reference angle. When you pull out your calculator to look for the value of theta or alpha or beta, you leave out the signage. So in your calculator, you do not put sine to the power of minus 1 times minus 0.65. No, you'll just put it as 0.65. The answer that you're getting is not necessarily your final answer. It is your reference angle. It is the answer that you will use to solve the rest of the problem, right? So when you put that in your calculator, you get a 40.54%, 54 degrees. And then here's where the sign comes into play. Your question, your initial equation was said that sine of alpha is a negative 0.65. Now you ask yourself, in which quadrant is sine negative? Let me just clear that out. Right, here we go. Then you go back and you say, in which quadrants is sine negative? This now is when you go back to taking into account your signage. And you know that sine is negative in the third and fourth quadrants. Then you go back and you say, what are the reduction formulas in those quadrants? Because now you need to express the sign accordingly, right? Quadrant, your reduction formula is 180 degrees plus alpha. So there we're going to substitute our alpha. If it is 100 and alpha is equal to 180 degrees plus 4.53. Let me say to you, this is very confusing. I've created a confusion. Let's call this x. X is the range of numbers we're looking for. I think it'll make things easier for you guys to understand if we use that, right? So then we're going to say that our x is equal to 180 degrees plus 40.54 in the third quadrant. So x again in the third quadrant will be 220.54 degrees. This is our first answer on when this could come out as true, right? Next we have our fourth quadrant. Our reduction formula in our fourth quadrant states that 360 degrees minus alpha will give us our answer. Here we substitute alpha, our reference angle, accordingly. Use x if you will, it will make things simpler to understand. And we find here that x is 319.46 degrees. And so what I'm saying to you guys is this and this are only two answers. 220.54% and 319.46%. These are our two answers within our given interval. Somebody might want to ask, why is 40.54 not part of the answer? Because at 40.54, that is, this angle sits in the first quadrant, and in the first quadrant, sine is positive. We are working with quadrants where sine is negative. That is the answer for that, guys. This is our first practice example. Reference point is practice example number 1, if you have a question on it. Practice example number 2. We have changed the range of our answer, and we've said that beta must sit between minus 360 degrees and 360 degrees, and we have said that both your start point and your end point are included, square bracket. This is our formula. Our formula says 3 tan of beta is equal to 20. Very simply, guys, as we've been doing in terms of resolving our equations, you'll divide both sides by 3. You'll write it simply. You could write it simply as tan beta being 6.666666. Or in your calculator, you can simply key it in as 10 to the power of minus 1 times 6.67, which will give you a value for beta, which is our reference point, our ref angle. It'll give you a value for beta of 81.47 degrees, right? Then we go back to asking ourselves, our beta, where is 10 positive? We're looking for signage in front of our equation. So we're looking for where 10 is positive. tan is positive in your first and your third quadrant, right? Let's address the third quadrant. Our third quadrant is 180 degrees plus beta. We're going to substitute our angle in there, our reference angle, and we're going to come out, apologies guys, this should be beta or even x if you want to make things easier. And we're going to come out at 261.47 degrees, right? So now I'm just, remember we've expanded our range. We have gone and included negative angles. So if we were stopping at 360 degrees, we literally would have both our answers. We would have our 81.47 and we would have our 261.47. But now we've included negative angles where we're going to start and we're basically moving backwards in our Cartesian plane, or you can reference it as to the left on our tan graph, right? And when we work with negative angles, we simply are going to subtract 360 from our reference angle, or our two angles that we have solved for that are positive. Because when you think about it, guys, if you think about it from a Cartesian plane perspective, when you say that you are working in negative, it's the equivalent of taking your y-axis and folding your paper over your y-axis. What happens when you fold your paper over your y-axis? You have a negative in your x-axis and all your other numbers remain. We'll go through that with time. We're going to spend another lesson, an additional lesson on this, and so just to ensure that you guys catch the principle of what I mean. So first here, we're solving for a negative angle. So our first negative angle comes to minus 278.52. This, please be aware, comes from the first quadrant, because we folded over our first quadrant, and the answer for that would have been this. And then this comes from our third quadrant, where the answer is this. And so from both, to get our negative angles, we subtract 360 and we get that, right? I'm expecting questions on this one, guys. So this is practice example number 2. Our final answer says that beta is equal to minus 278.53 minus 98.53, 81.47, and 261.47 degrees. So I'd like you guys to pull out a calculator, choose one of the 4 numbers in here, and key into your calculator tan of 81.47 or tan of minus 98.53, and you're going to find that your answer keeps going back to 66.67. Otherwise, you will say 3 tan of minus 278.53, for example, and your answer should go back to 20. This is our second example, guys. The main lessons that came from our second example should have been around moment you have negative angles and you will subtract, because now you are moving backwards, or you're moving all the way around. You are moving clockwise on your Cartesian plane, right? So we have basically established, I'm going to give you the method with which we were working so far to solve for our given intervals, what the steps that you will take in answering your questions, right? Step 1, you will determine your reference angle. Remember to use a positive value. This is why I was saying that even if you're having a sign of theta is equal to minus 0.3, you'll only use 0.3, leave out the minus. Right? Use your Cartesian plane to determine where the equation is true. When I say where the equation is true, I'm saying in the case of sine of theta is equal to minus 0.3, where is sine negative? So those are your quadrants that you are using. That is what step 2 means. Where is the equation true? In the quadrants where your negative or your positive applies accordingly. Step number 3, you will find the angles in the interval that satisfy the equation. That is what we've done when we said in the third quadrant such and such, and in the first quadrant such and such. And always, always, guys, check your answer back using the calculator. When you have an interval given to you, you basically have specific numbers. And I would say, take the time, guys, in your exam. You don't have to check all the numbers. Check 2 or 3 of the numbers. And if you keep getting the same vibe, you know that you've answered correctly. Take your answers using a calculator, and you write down your answer as shown in the example. You will say that your answer or your angle is equal to, and you will jot down 98.53 minus 278.53, 81.47. You will write it down number by number by number, right? Now we have our general solutions. So how do general solutions come about? As we were saying that our trigonometric functions on our graph could run for forever. They could run to infinity in either direction of positive angles. So when we don't have a restricted interval, we work with a general solution for the equation. A general solution simply means whatever number you put into k, which you will see as we go along, this equation will be true. Fundamental thing to mention, k is an element of integers. But let's check what we are talking about. Let's first start by then breaking down the methodology that you will look at when using general solutions, right? You will, number one, as you did in your interval, specific intervals, you'll determine your reference angle. You will use the Cartesian plane again to determine where the equation is correct and true. And then you will find angles in the interval, your interval being between 0 and 360. This is a normal Cartesian plane that satisfy this equation, after which you will add multiples for the period of each answer, right? What do I mean by that? One complete revolution or one complete period runs from 0 to 360. If you multiply 360 degrees by 2, you have gone to 720. 720, the values between 360 and 720 are another revolution, a completion of a cycle, and it's an entire go-around on a Cartesian plane. But you will see it as we work with our formulas. So when you substitute for k, when you multiply, when you add a number to k, you have been multiplying the number of periods, the number of full cycles, the number of revolutions of your trig function, right? 4 also goes back to check your answer using a calculator. Here you have an entire general solution. So you will substitute your k with a 1 or a 2 or a 3 quickly, just to make sure, check that your answer still is correct when relative to your equation. Finally, you will write down your answer in general solution form, which differs from your specific interval form, right? So I've put a practice example for us, guys, for this. I've said tan of 2 alpha minus 10 degrees is equal to 2.5. This, guys, is our angle. This whole thing here is our angle. I've written that very ugly. This whole thing over here is our angle, right? And we're going to solve. We're going to, in our calculator, look for the tan to the power of minus 1 of 2.5. And we're going to come out with that, 68.2. So here, sine of 2 alpha minus 10 degrees is 68.2. So what you do on the left, you do on the right. We need to get rid of this 2 alpha. Simply 68.2 degrees plus 10, which is 78.2 degrees. This, guys, is your reference angle. Yes, it's a double angle, and we'll work on it there. This is your reference angle. And then we go back to our usual question, our point 2, our step 2 on our method. Where is tan? Positive. And we know that tan is positive in the first and the third quadrant. In your first quadrant, Remember, our reference angle is not final alpha, it is 2 alpha, and we carry it down accordingly. So this is now how we write our solution here in this case. Confusion, I can only imagine. What we are looking at here, we are looking at the number of revolutions. Guys, we are looking at how many cycles you complete. So when I say look out for K, I meant that in K, you will substitute either by 1 for 1 complete cycle, you will substitute by 2 if you're completing 2 cycles, and that's if you're going up to 720 degrees, for example. So the purpose of this part here is really just to allow you to work within whatever range you want. Remember, we're using 360 because 360 takes us full circle. This is an entire period, an entire revolution. And so this K gives you the option of revolving more than once, gives you the option of continuing beyond 360 degrees. And let's say, for example, for whatever reason, you were going up to not 360, you were going up to 540, which is 1.5 revolutions. Then you would substitute 1.5 into K to check your answer, and it should still come out correct. Right. So at this level, alpha then is equal to, we're going to now remove the 2, divide everything by 2, everything. And so our general formula says that alpha is equal to 3.91 degrees plus K times 180 degrees. That 2, guys, will be divided by 2 because your angle is a double angle. We'll do more emphasis on that one later. Right? Then we have our third quadrant where our reduction formula is 180 plus alpha. So we're saying here 180 plus 2 plus 78.2 plus our usual here where our, let's call it a multiplier even though it's a plus, our multiplier to account for the number of revolutions, right? We solve that again, we simplify, and then we're going to divide by 2. What you do on the left, you do on the right, guys. And that leaves us with a formula that says 129.1 degrees plus K times 180 degrees. So what I'm saying to you is every time you substitute a number into K, let's say you want K to be a double revolution, you want to calculate in your, I would call it an 8th quadrant because you would have gone around the second time. So in your 4th quadrant, the second time, you want to calculate what the number would have been. Let's go back to when I'm talking about the 4th quadrant, the second time, I'm talking about on the slide. If you had to move beyond 360, as you know, your graph would start over and you'd end up in the exact same position at 720. 720 is a repeat of this entire thing. So it's a second period. That is what I mean when I say you complete a second revolution. Right? Going back to where we were though, on practice example number 3, we have found our general solution for practice example number 3. We have resolved for that. So because we're saying any number for K can fit in here, reminder, K must be an integer. We will write our answer as follows. Alpha is an element of 39.1 plus K times 180 degrees, or it's an element of 129.1 plus K times 180 degrees. Always state that K is an element of integers. This is literally your final answer. Your final answer is not an exact number. It is a solution or formula that allows you to be able to substitute any integer into this entire equation. Then when you get this number, take this number and put it in here, and your answer will consistently come out correct and true. Please give that a try with your calculators. If there's questions that we can't answer today, I'll definitely get to you tomorrow morning in those. All right, as usual, guys, my helpful links Siyavula, 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 guys. This is the textbook that I work from. This is the textbook that we work with. I've kept in your revision link and your new link and your Khan Academy for quizzes, right? So what have we done today? We have expressed and solved our trigonometric equations, one in specific angle answer, where you have the exact numbers like 22 degrees, 28 degrees, dot, dot, dot. And we have expressed, we've learned how to determine a general solution, where you are saying, I'm saying it's 120 plus k times 100 plus k times 360 degrees, because I'm saying if you put this in up to 720 degrees, you'll get the same answer. If you put it in beyond that, you'll still get the same answer. That's what that means, right? The main difference, guys, is really in your final answer, right? How you express your final answer. In the one, your final answer is exact numbers. In the other, your final answer is an expression that allows you to substitute any period. So tomorrow, guys, we'll be going through the homework examples I'm about to give you, and we'll be solving for quadratic equations. These are the homework questions that I'm giving you, guys. Just also in the interest of time, let me look at, I'll keep this on for a few minutes while you guys write down the questions. I'm looking for our Q&A, and I see, right, in the third quadrant, can't the formula be 270 minus alpha? It definitely can be. In one of our earlier lessons where we were looking at the Cartesian plane and how we reduce, I had said that because we're so used to working with 180 and 360 and 90, we wouldn't think that 270 is, but you are definitely on point. 270 degree minus alpha could be the reduction formula, in which case also remember your alpha must be an acute angle, right? Then Anonymous has asked an example, how many marks would practice example number 1 carry? Okay, I'll be back, guys. Let's go up quickly and say practice example number 1 in an exam would carry 3 to 4 marks. We're marking your method. We're going to mark, so first it's your recognition that this is a reference point is a mark, right? Even if your number wouldn't be correct. Number 2, the recognition that you are working with what quadrants your numbers are negative in is another mark. And then your application of your reduction formula is another mark. And your final answer is another mark. Your final answer need not be 100% correct if your reasoning flows through. So if you get 1 here as your answer and you substitute 1 in there, your final answer will be correct by virtue of you understanding how to do this. So it's about a 4-marker question. I hope that answers you, Anonymous. Let me go back to your questions, your homework questions, guys, because those are the questions we will be starting with tomorrow morning. From here, guys, our lesson is done. I'll see you guys tomorrow. Remember, you guys can hit me up on Twitter with your questions. _MbaliT is my handle. And please visit your Africa Teen Geeks pages. Tag us. Please extend our link to other people. Give people the link so that we can all get access to the lessons. Follow us on Twitter. Follow us on Facebook, on Instagram. You can even check out our videos on YouTube. We present live on YouTube. Okay, guys, our time is just about up. My usual ask of you guys, please take care of yourselves. Please be kinder to each other. Please keep up with whatever religious regimes that keep you strong, keep you safe, and be strong as we continue through this lockdown. Please do contact me, guys, if you need anything. Right? See you guys tomorrow, 8 o'clock sharp. Bring your calculators, bring your enthusiasm, and bring a fresh and willing to learn heart and mind. Bye, guys.